Let me to say one more thing about that question. It's a good question. I'll repeat it again. The question was, if a function has a subgradient at every point, does that imply it's convex? I think the answer is almost always, but not always. And the way that I would prove that, or what I would read to prove that, is that the existence of subgradients are implied by the supporting hyperplane theorem for convex sets. So you can always think of a convex function as a set in terms of the epigraph. We learned that connection already, right? Subgradients existing is an application of the supporting hyperplane theorem for convex sets. The supporting hyperplane theorem has a partial converse. So it tells you that if there's a supporting hyperplane at every point, and a few other technical conditions are met, then the set must be convex. So I would apply that logic just in terms of subgradients. So you would see that then supporting hyperplanes, which you think of as subgradients, imply convexity of the epigraph, or in turn the function, under some kind of minor conditions. So I think it's probably the answer is yes, but not always. Very good question. OK, let's go over a few connections, a connection of subgradients to convex geometry, and then some rules for subgradient calculus, and then some examples. See if we can get to that in the next bit. So the one interesting thing to do, and very useful thing to do, is to try to derive subgradients for the indicator function of convex sets. And you'll see why that's useful once we start talking about optimality conditions. So let's just consider a convex set C and the indicator function of that set, which is the set of all, the indicator function gives us 0 for all the points x that are in the set C, and infinity for all the points x that are outside of C. That's just, right? We've viewed this function before. It's written as I sub C of x. And this is a convex function when C is a convex set. That's what we learned, right? And it's very easy to prove that from the definition of convexity. So it has subgradients, therefore, right? Because it's a convex function. What are its subgradients? Well, for x that are in C, the subgradient of the indicator function at the point x is just the normal cone to the set C at the point x. That's something that we saw already when we talked about convex sets, normal cones. And just to remind you, that's the set of all g, such that the inner product of g with x versus g with any other y in the point, any other point y in the set C, is made biggest at x. Okay, so g transpose x has to be bigger than or equal to g transpose y for all y in the set. That's what any vector g that satisfies that is called a normal vector to the set C at the point x, and the collection of them is called the normal cone. So why is that true? Why is there this connection between this thing in convex geometry, the normal cone, and subgradients? Well, we just see it right from the definition of subgradients. Okay, we want, per its definition, to have the inequality indicator at y bigger than or equal to indicator at x plus g transpose y minus x to hold for all y at a particular point x. Okay, so we have to just think about this in two cases. If y is not in the set C, then the indicator of y, being the set, is always infinity, so it doesn't matter. That places no restrictions on g, because infinity is always bigger than or equal to anything. Right? So there's no restrictions placed on g from points y that are outside the set C. How about points y that are in the set C? That means we have to have 0 being bigger than or equal to 0, right, because x is in the set C, plus g transpose y minus x. In other words, g transpose y has to be smaller than or equal to g transpose x. But that's just exactly this condition. So it's exactly the condition of that makes a vector a normal to a set at the point x. Just rewritten. What happens if I ask you for the subgradient of the indicator at a point x that's not in the set? What are the only subgradients? What are there subgradients? Yeah.
Any constant line.
No. So what happens if I have y that's in the set, x that's outside of the set, and I try to make this inequality satisfied with a particular vector g. I can't do it, right? I have 0 being bigger than or equal to infinity plus something. So it's not going to work. So that's an example of a convex function that doesn't have a subgradient, but it's because this point x is not in its domain. So remember I said kind of subgradients always exist for convex functions on the relative interior of their domains. It's because if I take x outside of the set C, then the function is infinite, so it's really outside of its domain. So I'm actually asking for the subgradient outside of its domain that it may not exist. So subgradients are only guaranteed to exist on the interior of the domain of the function. That's just an example to see why that restriction is true. So a bit of a trick question. But this is just the picture of the normal cone. Okay, so just to remind you what normal vectors look like. We saw this picture already. If this is the set C, and I try to ask for a subgradient to the indicator function over this set, which is a function that looks as follows in R3. It's just 0 on this set, and it's infinity everywhere else. Then subgradients are just basically elements of the normal cone. That's exactly what they are. So the subgradient at this point, for example, would be just the cone containing it's anything in this cone, so any ray, but basically translated down to 0. Remember, because I've just put them up to the boundary so you can see normality pictorially. OK, so that's a nice connection to convex geometry, and we'll see that coming back. So some rules for subgradient calculus. These are basically things like what are the analogies of the chain rule, or for subgradients, or what are some rules for getting subgradients of compositions of functions if you know subgradients for the base functions. So unfortunately, we're somewhat limited in terms of our tools, not nearly as flexible as we are with gradients, but we still have enough tools to make a fairly decent theory for subgradient calculus that avoids us checking the definition a bunch of times. So here are the rules we know. If you have a function f, and you know its subgradients, and you ask for the subgradients of a times f, where a is positive, then you just scale the set, the subdifferential of f, to get the subdifferential of af. So this means a times any subgradient of f is a subgradient of the function af. Okay, so that's just a scaling rule. You can see that's true just by multiplying both sides of the subgradient inequality by a. And it's important a be positive, right? One trivial reason is that if a is negative and f was a convex function, then af would be concave. So we're not really staying within convex functions. Addition is also true. So the subdifferential of f1 plus f2 is just the sum of their subdifferentials. In other words, subgradients you get by just taking any subgradient of f1 and any subgradient of f2 and adding them together. So this is a set sum. Any element of the subdifferential of f1 plus any element of the subdifferential of f2. This is the closest thing to the chain rule we have for subgradients. It's the affine composition rule. And I think it's actually really useful. It's just that we don't have a more general version of the chain rule than this. We only have an idea of what happens if you compose functions with affine functions. So if I knew the subgradients of f, and I asked you to form a function g that was given by g of x is equal to f of ax plus b, versus some arbitrary affine transformation defined by a matrix A and a vector b, then the subgradients of g at a point x are just given by A transpose the subgradients of f at ax plus b. So you should convince yourself this is exactly the chain rule when f is smooth. This is exactly what the chain rule would give you when f is smooth. It should be A transpose times the gradient. That's all it's telling you. But the chain rule doesn't limit us, right, to composition with affine functions, but we are limited by that when we talk about subgradients. So these three are useful. We can use them and build up subgradients of more complicated functions from subgradients of simpler ones. This one's also very useful. It's a rule for getting the subgradients of pointwise maxima of convex functions if we know the subgradients of each of those individual functions. And it's actually just a generalization of that rule, that picture you saw, for two functions, f1 and f2, which we covered earlier on in the lecture. So if I define f to be a pointwise maximum of fi, so at every x, I just look at all my functions, f1 through fm, and I take whichever one achieves the biggest value, and I define that to be f of x, then the subgradients of f at x are given by the following expression. I just, at that x, look at all the functions that achieve the maximum. So this is all I, such that f of I is equal to f of x. These are functions that achieve the maximum. I take all of their subgradients at x, and I take the convex hull of all of those subgradients. That gives me the subgradients of f at x. OK, so let's ignore this outer convex hull. Makes the expression look more complicated. What happens if I just had one function that achieves the maximum at x? What do I get in that expression? I just get its subgradients at x, right? And if it were smooth, that just gives me back 1 point. There's only its gradient. So it's really just the rule we learned here, but generalized, right? If there's only one function that achieves the maximum, and say it was smooth, then the subgradient is just the gradient of that function that achieves the maximum. Here it's just a bit more general because I'm saying actually the subgradients are any of the subgradients of the function that achieves the maximum, because that function itself could be non-smooth. Now, if there's more than one function that achieves the maximum, then we're in that situation here, that kink point. And what we saw is that actually anything on the line segment between their gradients was a valid subgradient. It's really the same story here. We're saying we can take any subgradient from f1 and say any subgradient from f2 if f1 and f2 both achieve the max. And then look at this outer convex hull. We can take any, for example, convex combination of those subgradients, and it's still a valid subgradient. So the same picture that you saw before, just generalized to more than one function, and they're possibly non-smooth. So once you saw an expression like this, it's helpful to remember that the set of subgradients we learned, the subdifferential, is always a convex set, which means that if I told you, hey, the subgradients look like this, union of subgradients of active functions, you should tell me, well, that set's not convex, because we know subdifferentials are convex, so it has to be at least the convex hull of that set. Right? Because subgradients are always, the set of subgradients or the subdifferential is always a convex set. So even if you didn't think to remember to take convex combinations of functions from the definition of subgradients of the function in the definition, just at a high level, you know that the subdifferential is always a convex set. Right? So that there should always be some notion of convexity when you're talking about the subdifferential. OK. This rule is actually possible to generalize even beyond just a finite number of functions over which we take the maximum. And this one is going to be really useful when we talk in particular about norms. So this may look like an even more complicated expression. Really, I think the best way to remember this is for norms. OK, so if we have our function f defined as a maximum over, let's just say, fs at x, for all s in some set capital S, then that's more general than just a finite pointwise maximum, because I haven't told you that the set S is discrete. Okay? This could be, for example, an infinite set. It could be an uncountable set. I'm just taking the maximum of a bunch of functions over some index S. So first of all, we actually know that the resulting function is convex. We learned that in our convex functions lecture. You can take the maximum of any number of functions, doesn't matter how many. The result is always a convex function. So we're still well defined in that sense. And we basically have the same rule we had before, except for you don't always get an equality. We know that the set of subgradients at f at x at least includes the convex hull of the subgradients of active functions at x. I'm saying active to mean functions that achieve the max. So it's basically the same expression as before, except for it's not always true that we get an equality. And there's actually, what I noted here by CL means closure. So the convex hull in some kind of pathological cases may not be closed. So Remember, the subdifferential is always a closed and convex set. So those latter two operations, closure and convex sol, you can just think of as, we always know that the subdifferential is closed and convex. So we're just taking the same kind of intuition we had before and then using it to match what we know about subdifferentials.
Could you please give an example when the equality is not satisfied?
I don't have one off the top of my head. I don't think it's very useful to give such examples either. They're somewhat pathological. So for example, if S were compact and f of S were, I think, very weak conditions, like has to only be, it doesn't have to even be continuous in S. It can be like lower semi-continuous in S or something. Then you always get equality. So for most examples that you want to apply this to, you get an equality. For the examples which you don't get an equality, it's not really the end of the world, because we're going to see that a lot of the stuff that we do, you need to actually find subgradients. So you need to know the existence of subgradients, you need to construct them. If you don't characterize all the subgradients, you're not really at a loss. So I'm just telling you that these are all valid subgradients. We may have missed some. Usually, that doesn't matter. At least algorithmically, it doesn't matter. The most important case I think that's helpful to remember is the case of norms. So this actually gives the recipe for computing the subgradients of norms. And it's defined in terms of the dual norm. So when we talk about duality, we'll see this more explicitly. But you may have encountered this kind of thing in like a basic class on real analysis or measure theory that says that for every LP norm, let's say, there is a dual norm. And the dual norm is an LQ norm, so it's in the same class. And P and Q have the relationship 1 over P plus 1 over Q equals 1. Something that sometimes we call that complementary. So for example, if P is 2, its dual norm is still the L2 norm. It's self-dual, because 1 over 2 plus 1 over 2 is 1. Okay, so if P is 1, then its dual norm is given by Q equals 1 over 1 plus 1 over Q has to be equal to 1. What does Q have to be? Infinity, right? So the L1 norm is dual to the L infinity norm. Vice versa. If P was infinity, then Q had to be 1. Okay, so every norm has a dual norm. Well, that's true, but we're just saying every LP norm has a dual LQ norm where P and Q satisfy that relationship. Why that's useful is that you can actually define a norm in terms of its dual norm. We'll learn that when we talk about duality and see that in more detail. So for example, let's think about the L2 norm. The L2 norm is the maximum over all, at x, is the maximum over all vectors z that have L2 norm less than or equal to 1 of z transpose x. That's actually true. We know that's true. For example, what do we have to take z in order to get inequality here? So I'm telling you that, right, x, let's say 2, is equal to the maximum over all z with 2 norm less than or equal to 1 of z transpose x. What does z have to be to make that true?
X over x2 norm.
Yeah, right. So x, if we take z to be x over its 2 norm, then we get the, why did I say equals 1? I'm not sure why I wrote that. If we take z to be x over its 2 norm, then we get the equality there, right? So in general, this is true for any LP and LQ norm that are dual. So try out this. Try convincing yourself this is true for the L1 and the L infinity norms, for both the roles of P and Q there. That'll help kind of solidify this. So this is true, and like I said, we'll talk about that in more detail when we come to duality, the segment on duality. And from this, we can actually read off subgradients of any LP norm, because we actually just use this maximum rule. That's all we do. This is my function, f of x, and I'm defining it as the maximum of z transpose x over all z's that have q norm less than or equal to 1. Okay, that fits up into this framework here. Z is just playing the role of s. And fs of x is just s transpose x, or z transpose x. this is one of the cases I'm going to tell you where you get equality. So I'm just going to tell you that. In most cases you encounter, you'll get equality. So what we're told is that to take the subgradients of the LP norm, say, we need to first find all of the z's that make that achieve the maximum. So all of the z's that make z transpose x equal to the LP norm of x. And we have to take their subgradients with respect to x. And then we have to take the convex hull of that. And that gives us the subdifferential. So what is the, if I told you that, let's denote f sub z of x was z transpose x. What's the subgradient of this function with respect to x? What's the gradient of this function with respect to x? Z. Just a linear function. And it's an affine function, so it's clearly smooth. We took its gradient. That's the only subgradient. So what goes in the del of, or partial of f s x there is just one point, which is s, okay, or z for calling s equal to z. And that's actually just the argmax. That's the maximizer by definition, right? It's the point that makes z transpose x equal to the maximum. Z is just the argmax. And because it's a linear function, the convex hull doesn't really do anything. I mean, the convex hull of this set is the set itself. Okay, so the subgradients, this is the rule to remember, of the LP norm are the set of all z's that maximize z transpose x over all z's that have q norm less than or equal to 1. That's the rule for norms. So you can derive, for example, both of these directly from that rule. Right? That comes directly from applying that to the L2 norm. That comes directly from applying this to the L1 norm. Okay? All right. Why do we do this lecture on subgradients? Why do we kind of pause in our algorithms lecture? And why did I kind of continue to stress how important it was? There are two reasons why subgradients are important. And they have to do with analysis and optimization. We're going to see applications of both of these right away. So in terms of convex analysis, you can characterize optimality for convex functions in terms of subgradients. That's why they're so useful. And opens up a huge, very kind of powerful theory for optimality on which the KKT conditions are based, which we'll come to in great detail. There's also a very close relationship between subgradients and duality. So when we talk about deriving the duals of convex problems, knowing subgradients is invaluable for that. For the purposes of this current unit, so beyond today, you can think about the following motivation. If you can compute subgradients of a convex function, you can minimize it. That's pretty much always true. There's just very weak conditions on which that you have to place in the function to make that true. So think about gradient descent, where I place gradients with subgradients. That's really all we're going to talk about next time. We're going to see that actually that's a valid method for minimizing non-smooth convex functions. OK, so in the spirit of today's lecture, we're going to just kind of keep with some of the theory of subgradients. We're going to talk about the optimality condition you get from subgradients. So I claim that for any function, convex or not, any function, attaining the minimum of the function at a point x star is equivalent to 0 being a subgradient of the function at x star. I think when people see this for the first time, they are a bit shocked. This is maybe you're not shocked, but I was at least surprised when I saw this for the first time. If you could prove that your function that you cared about, no matter how complicated it is, had a subgradient of 0 at the point x star, you have the minimizer, the global minimizer, or a global minimizer if it's not unique. Okay, so this is called subgrading optimality. Think about what happens if f is convex and smooth. This is just saying something you already know, which is that 0 has to be equal to the gradient of f at x star in order for it to be minimized at x star. But it's just more general. So why is this the case? It's very easy. Just plug right 0 into the definition of a subgradient. If 0 is a subgradient, then it means that f of y is bigger than or equal to f of x star plus 0 transpose y minus x star. Of course, that 0 just means that f of y is bigger than or equal to f of x star for all y. So we have optimality, and the converse is true. From this, we can do very complicated things already. We can, if we wanted to, we could kind of go down this path and start deriving optimality rules for convex problems, for example, where we know that subgradients always exist. We're going to pause and do that later in the course. But I'm just going to give you a preview of some of the things you can say. So let's consider a constrained, let's say a smooth convex function constrained by C. That's going to be our minimization problem. We learned that, we never proved this, but we claimed this was true in the electron convex optimization basics, that this is an optimality condition for that type of problem. I have to have the gradient of f of x transpose y minus x being bigger than or equal to 0 for all y in the set C in order for x to be optimal. What it means, remember my high-level intuition was that what it means was that if you're at x and you try to move towards y and you check the gradient is telling you not to do that because it only increases in the direction from x to y. We can prove this directly from the definition from the subgrading optimality condition and what we've learned so far. So the proof of this is very straightforward. We're going to first recast the problem as f of x plus the indicator function that corresponds to the set C, right? Because this is going to be 0 when x is in the set C and infinity otherwise. We saw that we can always do that. And now I'm going to basically take subgradients of that function and say that in order for x to be optimal, we must have 0 being a subgradient. So just apply subgrading optimality. Well, everything on this slide we've learned in this lecture. The subgradient, the sum of two convex functions is the sum of their subgradients. Okay, so if I want 0 to be in the subgradient of f plus the indicator, then I can split up the set of subgradients. And because f is smooth, there's only one subgradient, and that's its gradient. And we already learned that, we proved, in fact, that the subgradients of the indicator function are just the normal cone to the set C at x. So what this says is that the negative gradient of f at x has to be an element of the normal cone. That's all we've said so far based on this subgradient optimality condition. And let's use the definition of the normal cone. It just means that the minus grad transpose x has to be bigger than or equal to minus grad transpose y for all y in the set by definition of the normal cone. And just rearranging that gives us this first order optimality condition. Just move x to this side, other side. Grad f transpose x to that side. Okay, so there's the first order condition for optimality, derived just in a few lines from the subgrading optimality condition. So even though this looks completely trivial, and its proof is completely trivial, we've already gotten something out of it that's quite, really quite sophisticated. It's a condition for optimality for smooth convex problems. And in fact, this condition, even if f itself weren't smooth, is a characterization for optimality that's fully general, right? Because we can represent any minimization problem in this form. Minimize some function subject to x lying in a constraint set. I can capture in that constraint set any number of constraints that I want. You know, I can represent gi of x is less than or equal to 0 for all I, and equality constraints, etc. So this is actually a fully general condition for optimality in a convex problem. That's not always easy to work with, this form. So later in the course, we're going to actually see the KKT conditions, which are essentially regurgitating this condition, but just in a different way that makes it easier to work with. OK. I have a few examples to go through, but we don't have a ton of time. And I think I'll just pick let me pick the here's what I'll do. Let me pick this example. And next time we'll come back and we'll talk about this stuff for the L1 norm. OK? So the function in question is the distance to a convex set. I suppose that's our function. We're going to skip through some details, but I'm going to show you how one would prove that the distance function has certain subgradients at a point x. So remember, the distance function to a convex set is defined as it's the minimizer, or it's the minimum value over all points y in the set of the two norms, say, of y minus x. That's the distance from x to the set C. It's convex, we learned that already, because C is a convex set. And this function, the two norm of y minus x, is convex in xy. And so it has subgradients. And now we might ask, what are they? What are its subgradients? We're going to prove only really one direction of this, so I'm just going to sketch out the proof since we don't have much time. But in fact, the other direction also is true. And this is a very interesting example where if you go through the logic on these next two slides carefully, you'll see that actually, if you're ever at a point that's outside of the set, so the distance from x to the set is positive, then there's only one subgradient. And that's this. It's x minus its projection onto the set. So that's the y that achieves the minimum, divided by the norm. And because there's only one subgradient, that means that the distance function is differentiable. OK, so if I asked you to prove that this was differentiable as a function of x, and that was like a problem you had on a calculus exam or something, that would be very complicated because of the minimum there. Right? But if we knew subgradients and we knew that was convex, then we can do that via this route. Only one subgradient must mean that that's the gradient. OK, so we're only going to sketch out the proof. And it's going to proceed like this. So we're going to prove that x minus its projection divided by the norm of that vector is a valid subgradient. So what we're going to the way we're going to do that is we're going to first write u to be the point that's closest to x in the set C. So that's actually the point that achieves the minimum there, right? That's the argmin. That's u. Quickly, let's just convince ourselves that that's actually unique. Why is that unique? It's because that criterion is strictly convex. That's a convex minimization problem. The criterion is strictly convex. Right? Just the L2 norm of y minus x. So as a function of y, the solution is unique, and that means it's just one solution. I'm calling that u. So by the first order optimality conditions for basically this problem, the ones we just learned, I'm just saying here that the gradient transpose y minus u has to be bigger than or equal to 0 for all y in the set. That's the condition for optimality of u. So we get that expression. And therefore, what this is telling us is that the set C is contained in a half space. So this is true for all y in the set. Right? U minus x transpose y minus u is bigger than or equal to 0 for all y in the set. Let's look at all the points y that make that true. That's actually a half space, right, by definition. And what we've just said here from the first order condition for optimality is that C is contained in the half space. OK? Now, using that, this is the part I'm going to wave my hands about, and drawing a picture, which I can do next time if we're interested in it, or I can just do it in office hours. Using this fact and some very basic geometry, we can actually prove that the distance from y to the set C is lower bounded by x minus u transpose y minus u over the norm of x minus u. OK, so I'm not going to prove that part. I'm just going to show you now how that gives you subgradients. So we've claimed that distance from y to the set C is basically lower bounded by this. Y minus u divided by the norm of x minus u. So I claim actually this just directly tells us that the vector in question is a valid subgradient just by rearranging. And all we have to do is in here, we're going to have to add x and subtract x. That's all we're going to do. So if we add and subtract x in this expression, which I claimed this came right from some very basic geometry, then you can see that the first term, I get exactly the norm of x minus u. Right? This guy, x minus u transpose itself over its norm is just the norm of x minus u. But that's the distance between x and the set, right? Because u is the closest point to x. And this term, I just get looking like x minus u versus norm transpose y minus x. This is exactly the expression for how a subgradient is defined. If that's g, this is saying the distance between y and c is bigger than or equal to the distance between x and c transpose plus g transpose y minus x. Okay, so it's exactly the conditions that are required to prove this is a subgradient. Okay, the other direction is true as well. So if that holds, then g must be that point. You can see that from kind of the basic arguments, which means that the distance function is differentiable. That's it. I will see you guys on Tuesday. Homework 3 is up, and the project milestone guidelines are also